Yes, we can have a review session for the test. That's a good idea. I was going to talk about it. We can discuss it now. Obviously, we can have the review session. So the exam is on Saturday. Let's see. You want to have one on Thursday, because I can't have one on Friday evening because I have something going on, the research group presentations. I know some of you have exams on Friday. So we can have it on Thursday sometime during the day. We can do Thursday evening. Start at 6 p.m. or something, or 7 p.m. after dinner, because everybody wants to eat dinner. Does that work for everyone? Thursday evening, 7 p.m. chemistry review session. Six works better for you. Problem is, it's dinner time for a lot of people. It's everybody at home. They're going to get angry with the chemistry professor taking, families away from their dinner table. And then instead of being blessed at the dinner table, when you guys are saying blessings, you'll be cursed at the dinner table. Just kidding. All right, let's do that. Put it on my calendar. Seven's dinner time for you. It's not a real dinner time. 6 is a real dinner time. I usually eat dinner at like 7 or 8 too, so it's in the middle of my dinner time. But I will sacrifice for the class and eat without my family. All right, so where did we leave off? Let me put this here. So we left off when we were balancing half reaction, making half reactions, and balancing half reactions. And we left off on this particular equation here. And so where we had manganese plus this sodium bismuth, I think it's bismuth, I'm not sure, I can't remember the exact term for BiO3. We went to bismuth 3 plus the manganese tetroxide anion plus sodium ion. And we had just covered and started discussing that you're going to make 2 half reactions from this, right? You're going to separate it into 2 half reactions, then you're going to balance the atoms other than oxygen and hydrogen. Then you're going to balance the oxygen and hydrogen using water and protons. Then you'll add electrons to balance the charges. Then you'll multiply by a common factor. And last, add the half reactions together, which requires the elimination of anything that's the same on both sides of the equation. And hopefully some people have started to put up their answers. So I suggested that you work on that before class today. I'm going to get going through it. Right, so if we do divide these reactions up into half reactions, I'm going to draw them down below. So first you would have, let me do something here. Move this over. All right. First thing we would have is our manganese as a 2+ ion is going to be going over to manganese O4-, right? If you divide up the half reaction, and you can see that's the first thing that happens. For the first half reaction is there. The second half reaction is you have the sodium bromate is then being converted over, I'm going to say bromate, bismuth. Oops, it's Bi, not Br. It's becoming bismuth 3 plus sodium ion. Right? Right, so you can see, obviously, in the first equation, the first step we do is we make the half reactions. Then we balance the atoms other than oxygen and hydrogen, right? We have one manganese on the left, there's one manganese on the right, so that's balanced. In the bottom equation, there's one sodium and one bismuth on both sides, so that's balanced from that perspective. Then you balance the oxygen and hydrogen using the water and the protons. Well, you can see here, we need to add 4 water molecules to the left-hand side to balance the number of oxygens that there are present on the right-hand side. Right. Then, in order for that to be balanced, we need to add 8 protons on the right-hand side to balance the hydrogens that are on the left. Right. We have 8 hydrogens here. We need 8 hydrogens on the left, on the right. The last thing we need to do is we need to balance balance the charges. Right. So we balance the charges here. So we have an overall 2+ charge on the left-hand side of the equation, right, coming from the manganese 2+ here. And on the right-hand side of the equation, we have an overall 7+ charge. So you need to add 5 more electrons to the right-hand side of the equation, so you end up with an overall 2+ charge on the right-hand side of the equation. Now, if we look at the second equation, right, in order to balance this equation, we need to now balance the oxygens. So we add 3 water molecules here. And once we do that, we see, okay, well, that means we need to balance the left-hand side of the equation by adding 6 protons. And now we just add up charges, balance charges. So there are 6 positives on the protons, or 6 positive charges on the left. There are 4 positive charges on the right-hand side. Right, so we need to add 2 electrons to the left-hand side to make that 4 positive charges on the left and 4 on the right. Right. So now we've balanced each of the half equations. Right. Now we need to balance the electrons between both of them. You can see there's 5 electrons in the first equation. There are 2 electrons in the second equation. So we can see how if we multiply the first equation, right, by 2, that'll give us 10 electrons there. We multiply the second equation by 5, that'll give us our 10 electron. Oops. Right, 10 electrons in the lower equation. So we need to do that. I'm not going to distribute. You should be able to distribute by now, but then you add up the equations. Right, once you add up the equations, you'll see that you'll end up with an equation that looks something like this here below. You'll have 8 water molecules plus 2 manganese 2+ plus 5 NaBiO3 plus, doing here plus plus 6H plus, that's what it is. Can't read my handwriting. 6H plus 10 electrons all goes over to the other side of the equation, which is 2MnO4 minus plus 16 protons plus 10 electrons. Did I do that right? 2. Oh, sorry, this is 30 electrons, not 30 protons. I can't read my handwriting. This is not 6 protons. Can't multiply. This is 30 protons. 30 protons there. Plus 5 Bi3 plus 5 sodium ions. I need to move something here. My screen. Plus 15 water molecules. All right, Now, once you've got to this point, now you've added the equations, you can see that you need to start eliminating, right? There's 10 electrons on both sides. Oops, let me do something a little different. Change the color here. All right, so we can cancel, and it'll be easier to see. That's right, we need to cancel the 10 electrons on both sides of the equation. All right, we have 8 water molecules on the left. They're going to cancel out 8 on the right, so we're going to be left with 7. All right, we need to cancel out there. And if you wanted to fully balance the equation, and you'd have 16 protons on the left, and this would balance out. It would leave you 14 protons on the left, and the rest of the equation would be balanced. And the question then therefore asks is, in particular, talking about how many water molecules are there in the balanced equation for the reaction with the small whole number coefficients. And you need to realize that it's going to be 7 because we needed to eliminate, water on both sides. So everybody hopefully got D as their answer. Right. Any questions on that? Any questions? Pop them in the box. All right. Right. It's finished an equation with balancing equations, yeah. Just close to where we started. It's just a more complicated equations. All right, balancing in basic solution. So a reaction that occurs in basic solution can be balanced as if it occurred in an acid solution or an acidic solution. Once the equation is balanced, add OH to each side to neutralize the H plus in the equation and create water in its place. If this produces water on both sides, subtract the water from each side so that it appears on only one side of the equation. So what does that mean? So if we're going to be doing a basic reaction, here's another example. Right. The first thing you're going to do is you're going to go through the first steps of the procedure as if the reaction were occurring in acidic solution, right? You pretend it's acidic first. So you go through, we're trying to balance it. It tells you it's a basic solution, but we pretend it's acidic at first. We do everything we just did in that problem. We then add the appropriate number of hydroxide ions to each side of the equation, and we're going to combine any protons with hydroxide ions to form water, and then just simplify the equation, right? So we take the half reactions first. That's step 1. And I'm not going to go through each of the individual steps here. Just, obviously you can take a look at the half reactions. Then we're going to balance the half reactions as if it took place in acidic solution, right? We added water to balance the oxygens on the other side of the equation. We then add protons to balance the hydrogen atoms from the water. Same thing in the bottom equation, right? We added water and then we added protons. Now, the next step is where you need to add an extra step. So now we need to neutralize the acid that's in solution, right? So we have these 2 protons here. We need to add 2 hydroxide molecules to both sides of the equation. You can see it's added to both sides. Because remember, this equation is just, think of an arrow as just an equal sign. So what you do to one side, you have to do to the other side. So you add hydroxide to both sides. Then you do the same thing for the second equation. You have 4 protons, you add 4 hydroxides to both sides. Once you then add the equation, you can see, add the proton and the hydroxide, you can see you basically created 2 water molecules there. You did the same thing here. We add these 2, we end up with 4 water molecules. But since there's a water molecule on both sides of the equation, now you can see that what we do before we go on to the next step is we need to cancel the water, right? We cancel 1 water on both sides. We're left with 1 here. On this, in the lower equation, we cancel 2 water molecules. So we're left with 2 water molecules here. And that's the equation that we end up with down below, right? So the protons are there. The hydroxide, you can see, is now on the other side of the equation. So you can see one of the differences between an acidic reaction and a basic reaction is the acid reacts with the opposite side of the equation, whereas the base, versus the base. You add 2 hydroxides because you have 2 protons, right? So you need to neutralize. When you're thinking neutralize, think of the reaction, right? You have acid plus base going to water. That's just the neutralization reaction. That's all we're talking about. So if you have 2 protons, right, then you need 2 hydroxides and you get 2 waters, right? If you have 6, then you need 6 and then you get 6. That's all we're talking about here. All right, so you can see now that once you've gone through and balanced the equation, you've canceled out any extra waters. The next part is going to be, balancing the charges, right? So you have 2 electrons here on the upper equation, 3 electrons on the lower equation, and that's all you do is you basically, multiply. Obviously, the first equation is going to be multiplied by 3. Second equation is going to be multiplied by 2. And that's what they give you out as an equation here. Then you add both of those equations together and eliminate the extra electrons, and you end up with the overall equation shown here, where you can see once you do that, right, this equation is going to end up, and they don't show it here, but this equation is going to end up with 6 hydroxide on the left-hand side of the equation and 8 hydroxide on the right-hand side of the equation, right? Because there's 6 and 8. And so you're going to need to cancel these. You're left with just 2 here, right? So this is where these 2 hydroxides come from, right? And the same thing goes for the water. You do the same thing for the water. You have 3 waters on the left, 4 waters on the, 3 waters on the right, 4 waters on the left, and you end up with an overall 1 water on the left. All right, so that's kind of the stepwise process. It looks exactly the same. You just add in everything on this previous slide. You need to neutralize the protons that are present when it says basic solution. All right. And then you can do the double check, right? You can double check that they're correct number of carbons, nitrogens, hydrogens, oxygens, manganese ions on both sides, and then the charge is equal on both sides of the equation. So that's the last and final check, is double check. Make sure everything is balanced, truly balanced. Otherwise, you might have made a mistake. Or just, you might not have multiplied. The most common thing you probably find is people are going to try to skip out drawing out the step here after the multiplication all the way through. I tried doing that in a problem, and just the last problem that we worked through. And I made all kinds of mistakes as I was working through. Really, I recognized them, but I made them nonetheless. So draw the extra steps out. It's my advice to you. All right. All right. So they want to bring your attention this, the fact that you run this, draw the reaction as if there were protons involved does not mean that there are protons involved in the chemical reaction, right? In the end, there are hydroxide molecules involved in the chemical reaction, right? That's what's being shown here. Okay. So in this, under basic conditions, right, you're going to have just, hydroxide ions present. All right. Voltaic cells. So in spontaneous redox reactions, electrons are transferred and energy is released. That energy can do work if the electrons flow through an external device. This is a voltaic cell, also known as a galvanic cell, right? So you might have heard galvanic cell somewhere along the line when you were a kid, or a voltaic cell. So voltaic cells, we're basically talking about chemical reactions. So they're showing you a chemical reaction here, where there are 2 solutions in this flask, right? And they're in contact with each other. There's a porous glass frit in between each of them. I'm down on the lower section here. And so there's, they're basically able to transfer ions or charges, between, or ions in between this glass frit. You can see how the colors stay separated between both sides. In this case, they have a zinc electrode on the left and a copper electrode on the right. So we're going to talk a little bit more about the details about how these work. Because you can see here, there's an electric current, right? 1.10 volts of electricity is running through from one side to the other here. Okay, let's make sure. So we're talking about voltaic cells. So here's another thing you need to memorize, is that oxidation occurs at the anode and reduction occurs at the cathode. And the easiest way to remember which is the anode that I could think of was that recognizing that these are both vowels, right? You have O and A are both vowels, and then reduction occurs at the cathode because they're both consonants, right? You have the A, R, and the C. I couldn't come up with a mnemonic. I did try and search in the past, trying to figure out if there was one, but trying to remember which is an anode and which is the cathode. This is about all I could come up with. Feel free to come up with your own way of memorizing and linking these, right? So you have, your other mnemonics, right? You have oil rig, and then you could say oil rig with the anode and cathode, and then you have Leo, right? And Gur. And then you have their anode and the cathode. But I couldn't come up with anything about how to make those into anything more complicated or something more interesting, but feel free. But you can see how you need to link the two. Do you get extra credit if you come up with a good one? Well, you could publish it on the web and see if people use it, and then you could get recognition. Make a little tiny placard, post it on Facebook, and see if you go down in history as, the person who made up the new mnemonic. I wouldn't waste your time. So no, yes. Correct, Jason. You don't like my vowels there? I'll hunt you down, Annie. All right. So when electrons flow, charges aren't balanced. So a salt bridge is usually a U-shaped tube that contains a salt agar solution is used to keep the charges balanced. Right. So what they're talking about here is we have an electric reaction occurring here, right? Where we have the zinc is reacting to give us zinc ions plus 2 electrons, right? You can see in solution, we have this zinc, the surface of the zinc here is reacting, giving off 2 electrons. Those 2 electrons, right, are traveling all the way around, and then they end up entering into the solution and reacting with the protons, right? There are some protons floating in solution here. So at this cathode, so right, the zinc is the anode, where the oxidation is occurring. So at the cathode here on the other end, we have the high protons are reacting at the cathode with 2 electrons, and they're forming hydrogen gas, and they're showing you little hydrogen gas bubbles that are being formed here. But obviously what's going on here is unbalanced, because you're taking protons, right, charged ions, and you're turning them into neutral molecule on the right-hand side, whereas on the left-hand side you have a neutral molecule that is becoming charged. So the salt bridge that's showing you here in the center shows you what's going on, right? We have a salt bridge, which means our nitrate ions that are in solution are going to travel up into the salt bridge, and they're going to work their way around and eventually enter to the opposite side to interact with the zinc ions that are being formed in solution, right? So you can see there's you end up having, nitrate ions enter, right? They're sodium ions. They show with an arrow. I disagree. The sodium the ions aren't really moving. They're just sitting there in place. It's the nitrate ions that are moving, and they're moving from one side to the other. All right. So In voltaic cells, so in the cell, electrons leave the anode and flow through the wire to the cathode. So that's what they're telling you here, right? So when we're looking at our voltaic cell, you have electrons leaving the anode, the negative side, and they're moving towards the cathode, or the more positive side of the reaction, right? So the electrons travel from anode to cathode. And if you think about, that means, obviously, because it's oxidation that's occurring here, oxidation means electrons are being generated, right, on this side, whereas those electrons are being consumed on the cathode side. So cations are formed in the anode compartment, and right, so we have cations being formed in the anode compartment. So as the electrons reach the cathode, cations in the solution are attracted to the now negative cathode, and then the cations gain electrons and are deposited as metal on the cathode. So what they're talking about is, we have, in this particular example, you have, cations that are going to be start to deposit on the cathode. So has anybody ever had an electroplated metal, something that's been, plated of some type of plating solution, that they plate, metals, coatings on other more reactive metals frequently by, essentially sending a charge through this. A reaction that you can do with this is you can coat pennies, copper pennies, in zinc. I know that's a experiment Dr. Branish has done in the past. So you can make silver pennies. So the cations that are in here that are traveling through this porous barrier or salt bridge, these are just cations that are in solution. So I don't think this is not a very good picture of actually what's going on, because these cations that are being formed at the anode are not the cations that are traveling over to the other side per se. They don't have to be the cations that are being traveling on the other side. You could already have other cations in solution, right? So you could already have some other cations in solution on this right-hand side of the porous barrier, right? So there already could be some metal. It's supposed to be M plus. But they are heading towards the negative charge, correct? Whether those cations in solution that are being produced on the left-hand side are doing it or not is probably not likely, but it could be. It depends on the reaction. It does mean that the cations are moving to the right, just due to diffusion. They're going to, right? If you have a large, buildup of cations on the left, they're going to diffuse to the right. For example, in this salt bridge here, right down in the picture down below, you have zinc ions are being formed, and those zinc ions are moving towards the this salt bridge. But the actual, if the zinc ions are moving, they're going to be moving because of diffusion, primarily because of diffusion. So they're going to be displacing the sodium ions, and it's the sodium ions that are eventually going to end up in solution here down below. So that's why I'm saying it's not, it depends on the chemical reaction that's occurring and what you have in the salt bridge. There's lots of variables to determine what's going on. It's not perfectly straightforward that that's exactly what's going on, that just the cations are plating from one side to the other, but it could be. There's no real good, I tried finding other better pictures in the past for this, and there really isn't a good picture to try to explain this. All right, so let's go through an example and describe a voltaic cell. So the oxidation reduction reaction of chromium Cr2O27, O72- is the chromate ion, is reacting with 14 protons and 6 iodide ions to form chromium in the 3+ state, plus elemental iodine plus water. So this is a spontaneous reaction. So they're telling you that this is going to work in the forward direction, right? Solution, So what they're doing is they're explaining what they're doing, right? They're dissolving potassium chromate, right? Which is obviously where these ions come from, right? Potassium is just the spectator ion in the reaction, plus sulfuric acid, right? Which is where these protons come from, right? The sulfate is just a spectator ion. They're pouring both of these into one beaker, and a solution of potassium iodide is poured into another, right? So they have two separate beakers. One, they have the chromate and the protons. The other one is where the iodide is. They add a salt bridge to join the beakers, and then they have a metallic conductor that will not react with either solution, such as platinum foil is suspended in each solution. Right? The two conductors are connected with wires through a voltmeter or some other device to detect the electric current, and the resulting voltaic cell generates an electric current. And it says indicate the reaction occurring at the anode, which reactions occurring at the anode, which reactions are occurring at the cathode, the direction of the electron migration, and the signs of the electrodes, right? So we're going to go through and walk through what this means. The first step you need to do is you're going to divide the chemical equation into half reactions, right? So the first thing, half reactions first. So you can identify the oxidation and the reduction processes. Then you're going to use the definition of anode and cathode and other terminologies that are summarized in figure 20.6, which is this figure right here. This is figure 20.6 on the right. So in one half reaction, you have the chromate ion as an aqueous solution is converted into the chromium-3 ion as an aqueous solution. And you're going to start with these ions and then completing and balancing the half reactions. You have, right, the chromate ion reacts with 14 protons plus 6 electrons. They are chromium-3 plus and are 7 water molecules. So obviously you could have just this step started with Cr2O7, 2 minus, moving on to 2Cr. Actually, probably just moving into 2Cr3 plus, right? And then we just went through all of the steps we did in the last problems to balance this and get this final equation. In the other half reaction, we did the same thing, right? We have iodine being converted over to iodide being converted over to iodine, right? And all we did was balance. And you can see in this case, there's no need for water or protons because you're just going from one to the other. So it's just electrons that are being transferred over. And, this equation has already balanced between 6 electrons. So the first half reaction is the reduction process. The electrons on the reactant side of the equation. And by definition, the reduction process occurs at the anode, right? So we have our reduction is occurring at the anode. So if we go back to that reaction, right? Because we're adding electrons, right? We're talking about the if you think of oil rig, right? You have oil rig, right? With the oil rig description, we have the gaining of electrons, right? Right, this is the gaining of electrons. So we have the reduction as the first equation. And we know that that is going to be occurring at the cathode. So we have that occurring at the cathode. So the first equation is occurring at the surface of the cathode on the right-hand side. The second half reaction is the oxidation process, right? The electrons are on the product side. With the oil rig description, right? Loss is on the right-hand side. And so therefore you're going to have that reaction occurring at the anode, which is on the left-hand side of the equation. So the iodide ions are the source of electrons, and the chromate ions accept the electrons. Hence the electrons flow through the external circuit from the electrode immersed in the potassium iodide solution, the anode, to the electrode immersed in the potassium chromate sulfuric acid solution. So what we figured out is we have our iodide. Oops. Right, we have our iodide is sitting in solution here, and we have our chromate. Chromate ion is over here on this side. Why is this not working? I lost my pen. So we have our chromate occurring on the other side here. Oops. Right, and in this side we have protons as well. Oh, we have a whole bunch of comments here. Sorry, I didn't see them. Let's see, what is everyone saying? Yes, can you come in? You heard my little son asking to come in. You want to see my kids? Nope, keep them off the television. Just kidding. But no. Yep. All right. So when we're looking at these particular reactions, right, the only thing that's happened is that these electrons, right, the electrons are moving from one side to the other. Both the cathode and the anode themselves, so the rods that are sitting in solution here, these solutions are not going to be reacting at all in this particular reaction, right? There's nothing going on for this particular reaction. They're going to be simply providing a means of transferring electrons from one side of the solution to the other side of the solution. And the cations are going to move through the solutions toward the cathode, and the anions are going to move towards the anode, right? So that's all that's going to be going on here is we have this movement that's going to be occurring, to essentially balance, the charges on both sides of the porous salt barrier. Right, and then anode from which the electrons move is the negative electrode, and then the cathode to which the electrons move is the positive electrode, right? So the anode ends up being negative, right, because that's where the electrons, right, this is where the electrons are being generated from the iodide being converted over to iodine, and then the cathode is where it's moving towards, right, which makes sense. The negative charges are attracted towards the positive side. All right. I can't remember if I have a sample for this one. Right, let's do a quick sample. I skipped one of the sample problems. We're going to do a different one. Let's share this. Okay, so do a quick problem here. See if everybody understands what's going on. It says the following two half reactions occur in a voltaic cell. We have nickel as a solid is converted over nickel ion plus 2 electrons, and then copper 2 plus 2 electrons is converted to copper as a solid. Which of the following descriptions most accurately describes what is occurring in the half cell containing the copper electrode and the copper 2 plus aqueous solution? So think about that. What do you think the answer is going to be? think of the picture of the cathode and the anode solution. What's going on, right? You have your anode on one side, negatively charged, right? And you have that in some solution, and that's traveling. Electrons are traveling over, right, to the cathode on the other side. Positive charge, right? So we're saying that we're looking at trying to figure out, you have two containers, right? And they're connected with the salt bridge. And you're trying to figure out which reaction is this occurring at. And they're asking specifically about the copper electrode. All right, so you have a copper electrode. So the copper is, all right, what's occurring to the copper? What's working on? It's gaining electrons. Does that occur at the cathode or the anode? Go for which was easier to switch between these two. Actually, do I have 6 minutes? Right. The electrons are moving towards the cathode, right, on the right-hand side. And what's happening to, let me go back, actually, it might be easier if I go to a different slide. I guess there isn't a really good one. So if it's occurring at the cathode, fortunately, there's not a good slide. Right, so if you have copper 2 plus 2 electrons going to copper metal, right? So if this is copper 2 plus in solution here, and you have a copper electrode here, right? So this copper 2 plus is obviously depositing itself onto the metal rod, right? Because it's being converted to copper metal, right? In solution, because as the electrons travel from one side over to the other, right, as these electrons are moving, they then react with the copper 2 plus in solution, and copper metal comes precipitating or crashes out of solution onto the cathode. So we know that it's going to be gaining mass. So then it's therefore either going to be B or D, right? Because we're increasing the amount of copper metal on the cathode. So the next question is what's happening at the salt bridge? If you have metal ions are being consumed, the 2 plus ions are being consumed here. On the other side, you have, right, the nickel going to nickel 2 plus. Oops, not 2 nickels. Nickel 2 plus plus 2 electrons, right, on the other side. So you're forming ions on this side, right? So this nickel here, the nickel rod, right? If you had a nickel rod here in solution, that nickel rod would be shooting off, so to speak. It's supposed to be an arrow. It's a really bad arrow. You'd have nickel 2 plus ions falling off of this, right? Being formed in solution. So you have lots of charge on this side, so you can imagine these nickel ions are going to start heading up that way, and then therefore are going to be traveling around this way, right? So you can see that what's going to be going on is, right, we have the nickel 2+ ions are moving towards the area where you're going to have less charged copper 2+ on the right-hand side as it's being consumed. So we have cations from the salt bridge are flowing into the half cell. So it's going to be B. So sorry, everyone. I don't think anyone got it right. Does it make sense, though? Any questions on that? Great job, Brian. All right. Oops. All right. So why are we interested in these particular chemical reactions? And the reason we're interested in, electrochemistry is because of the electromotive force, right? Oops. Pen off again. All right. The electromotive force. And so we're interested in the electromotive force because you think, thinking about it, right? It's just kind of just like a waterfall. Water will flow spontaneous in one way in the waterfall. Comparably, electrons flow spontaneously one way in a redox reaction from high to low potential energy, right? So if you think about your anode, right? Your anode is where those electrons are being produced, right? You have some, you have your so my thing just lost picture, right? So you have these electrons that are being formed, right? And those electrons kind of fall down the hill, so to speak, like a waterfall heading towards the cathode. And so you have a high potential energy at the oxidation side and a low potential energy at the reduction side. So you have this natural transfer of electrons that occur, and we leverage the electrons in the form of, all of our electrical devices, whether that's a light bulb or computer screen or, a fan, anything that's running off electrical power is going to be running through this. So the electromotive force is the potential difference between the anode and the cathode in the cell, right? So the potential difference is also called the cell potential and is designated as the energy of the cell, the E of the cell, right? It's the electromotive force. It's the amount of potential energy that a cell, when we're talking a cell, we're talking about an electric cell, has to do work, basically. It's measured in volts, right? We measure all of our electricity in volts, where 1 volt is 1 joule per coulomb, right? These are joule coulombs. This is the measurement of what a volt is. Standard reduction potentials. So reduction potentials for many electrodes have been measured and tabulated. The values are compared to the reduction of hydrogen as a standard. So everything refers back to hydrogen as a standard. And the standard conditions, right? This is always being run at standard conditions. 1 molar, 1 atmosphere, 25 degrees Celsius. So when we're looking at our standard reduction potentials, we're always talking about standard conditions. So there's a picture of what this is right here, right? These are our standard reduction potentials in water at 25 degrees Celsius. So you can see there are lots of different, equations here. We'll come back and we'll be using these. I'm not going to go through each of them right now, but just want you to recognize that you can see something with a very large positive charge, this fluorine reacting with 2 electrons to give fluoride ions, right? This reduction is very favorable, right? It's got a plus 2.87. So it's a very favorable reaction. So fluorine as a gas will react very readily with 2 electrons to give us fluoride ions. Look at the next slide. So this is a continuation of that table. And what I want to point out here is the standard reduction potential is at 0 is the standard reduction potential between 2 protons reacting with 2 electrons to give us hydrogen gas. So this is arbitrarily defined. That's why they write the word defined here. So we compare everything to this particular reduction. The reduction of two hydrogen atoms, proton atoms, reacting with two electrons to give us hydrogen, elemental hydrogen, is arbitrarily described as 0. So everything else is compared to this. So when we see this plus 2.87, it just means it's 2.87 volts higher or more favorable than hydrogen, right? This one here, the copper one, that's 0.34, is 0.3 volts more favorable than the hydrogen reaction. That's all this means. Whereas if we go to the next page here, you can see the lithium reaction. So lithium reacting with one electron to form lithium solid at a negative 3.5 is 3.05 volts less favorable than a proton gaining electrons, which makes sense, right? We've talked about, group 1 metals. Group 1 metals prefer to exist as ions. We've talked about how explosive they can be as pure metals, right? They don't like to exist as their pure metals. They prefer to exist as ions. So that would make sense that the reverse of this reaction is going to be favorable, whereas the forward reaction is not. So how can we use this? The standard hydrogen electrode, right? It's just going to use this for comparison. This is the reference cell. This is the thing that everything else is compared to. And by definition, as the standard, the reduction potential for hydrogen is going to be given 0. This is, because it's a standard, we set it to 0. And all that's going on here is they have a metal rod here, and then this little platinum surface. And at the platinum surface, you can have, if you're pushing hydrogen gas into this cylinder, right? There's hydrogen gas entering in the cylinder. The hydrogen gas molecules are going to come in contact with this platinum surface, and there's going to be an oxidation event occurring, right? At that surface, you have oxidation occurs, and you're going to be releasing protons, H+ ions. And this is going to be what it looks like when you have this standard hydrogen electrode as the anode, right? Because the anode, you have oxidation occurring. Also, at that surface, if you were thinking about what would be going, if you're going to think of this as a cathode, which is the other, right? If you had protons in solution, those protons can come in contact with this platinum surface, and they can gain electrons. And when they gain electrons and the reduction process occurs, and these hydrogen atoms, molecules are released. So when you think of the standard hydrogen electrode as a cathode, you have protons being reduced to hydrogens, right? So it can go in either direction. That's all I'm trying to say is when we're looking at these tables here, this reaction that we see is the reduction half potential. This is what happens when you have a gain of electrons, right? But you can invert the reaction and have an oxidation occur with the same exact reaction. And this is how we're going to use this table. All right, so this particular reaction, right, you have two protons as an aqueous solution that's 1 molar, can react with 2 electrons to give us hydrogen as a gas at 1 atmosphere, right? This is the standard, reduction potential of a hydrogen, and protons interacting, going back and forth between one another. You need a 1 molar solution and a 1 atmosphere of pressure. So how do you use these, take advantage of these and use these use the standard reduction potentials in a useful way? What we can do is we can calculate the standard reduction potential of a particular cell by looking at the reduction that's occurring at the cathode and subtracting from that the energy of the reduction that's occurring at the anode. Obviously, at the anode, this is an oxidation, right? But the number that we're using for the cell is the reduction potential numbers. So all we're doing is we're going to calculate, in order to calculate the energy of the cell, we're just taking the reduction potential of the cathode and subtracting the reduction potential of the anode. So because cell potential is based on the potential energy per unit of charge, it's an intensive property. And then let me go through what this means, right? An intensive quantity is one whose magnitude is independent of the size of the system. For example, right, temperature, density. Temperatures and densities don't change just because you have more of a substance. The same thing goes for, cell potentials. Cell potential stays the same no matter how much of that you have. Whereas an extensive quantity is one whose magnitude is additive for subsystems, right? Mass. The more of a substance you have, the larger its mass, right? The more of a substance you have, the larger its volume. So directly correlative. They're extensive properties. Here. All right, and you just think about it this way. If you have I won't try to pick on anybody, I'll pick on myself. If you have a Toyota Camry and you put that Toyota Camry at a stop sign and you take off as fast as you can go, you can only go as fast as the Camry goes, right? If I add, put 3 Camrys in a row and connected them all, welded them all together, and still tried to accelerate, the acceleration is not going to get any faster because the weight of all the Camrys is still there, and the amount of acceleration that each motor has is exactly the same. Right? Think of it that way. That's basically what we're talking about here. When we're talking about the energy of the cell, right? You can have 6, 7, 8 batteries all linked up together, and if you do that, your amount of energy that exists, right? You could have a battery that's, 3 pounds or 300 pounds. It doesn't make a difference. The amount of energy that that cell is going to produce, the number of volts of energy that a system is going to produce is always going to be the same. There are ways, obviously, to link batteries together to change that, but that's not what we're talking about here. All right. So what we have here are the cell potentials, right? And this is meant to be set up like the waterfall effect, right? Where we have our anode, right? At the anode, we have our oxidation occurring. And at the cathode, we have our reduction occurring, right? So down below. And the electrons are being formed in the first reaction, and then they, kind of flow downwards towards the cathode, right? So, and the gap that exists between these two is the standard reduction potential of that cell, right? So what we're doing is we're going to take the energy of the cell, and we're going to take the energy of the cathode, right? And we're going to subtract the energy of the standard reduction potential of the anode, right? So in this case, if we look at our table, right, the reaction that we're looking at is the zinc reaction. If we go back, right here, that's this one in the table right there, right? So you can see the reaction that's occurring here is a reduction, right? You have zinc 2 plus 2 electrons moving to zinc. And in this particular reaction, the reduction is minus 0.76. So pay attention to what we're doing. We're still going to use this number, even though we're going to turn this equation in the opposite direction, right? If we look at what's going on here, right, we have the opposite equation that's occurring here, but that doesn't make a difference. We're still going to subtract the negative 0.76 in the equation. So you want to make sure, I'm just trying to point out, you don't invert. See, when you do that, this standard reduction where the zinc is going to transfer electrons very rapidly over to the copper on the opposite side, right? The copper is going to pick up those 2 electrons and form elemental copper. So you have a very rapid plating event occur, and you can see for this particular reaction, you have a standard reduction potential of 1.0 0.1 volts of electricity being formed. All right. I'm not going to go through. We have like 2 minutes left of class. So I've discussed through 20.5, so I will basically, I'm not going to go through the example, but that's basically the example is what I was just discussing there. I'm just trying to think for the exam. So 20.5 and 20.6 will be included, because this is all through this section right here. It's not complicated stuff. I hope you don't think this is complicated. So up through 20.7, it's free game. All right. So I will include up through section 20 point exit sample exercise 20.7 on the exam, the final. So no, this is an actual oxidation reaction, right? This is an oil, right? Oil rig. So this is the oil side, this is the rig side down here. What I said was you use the standard reduction potential number. So you use the reduction number in the equation here, even though this is an oxidation reaction that's occurring. So the anode always is going to have an oxidation occurring, but when you're calculating the standard reduction potential of the cell, you're always going to use the numbers for the reduction in your math. Well, you can just complete, Freddie, you just complete the homework section up to wherever you want, and once you submit, actually, I'm not going to have a due date. I'll probably just release the answer key, and you can the homework's not going to be due. The last one isn't going to be due anyway. So if I haven't, I'll release the answer key after this. And we'll have a review on Thursday at 7 p.m. Thanks, everybody. If you haven't filled out your review for the class, please do so. I appreciate it. That would be helpful. Only good things to say, of course. Thanks, everyone.